So indeed, I'm extremely happy to be here with Milo. We had a wonderful time here in August, and we will be back. So, in particular, with this opportunity of the Onsager Professorship, it happens that Onsager is one of my heroes. It's basically my hero. After Dan, of course. But
The other day we had to go back to Onsager because he's my hero too.
But truly speaking, I mean, anyway, so I will be discussing indeed some aspect of fluid flow at nanoscale. So it's a topics which we are studying a lot in Paris. And here today we'll be presenting it more in the context of a problem of osmotic energy harvesting and desalination. So I will make a small detour, and then at the end I will come back to that. But just to give you the idea of osmotic energy, and here in Norway, it's very special. I mean, because Norway was the pioneer in this osmotic energy, and I will come back to that. So basically, the osmotic energy is the dream of harvesting entropy. It's basically when you have a difference of enthalpy between seawater and fresh water, which is in the range of 1 kilowatt-hour per cubic meter. So this is energetic, typical units, strange units anyway. That's very small. I mean, it's basically the energy contained in 100 grams of butter. But at the same time, it's large because it's basically the hydraulic energy, gravitational energy that you have with a dam of 100 meters, which is not so small as well. But it's small, but you have huge flux of rivers going into the sea all over the world. And of course, I give you here a not typical example, which is the Amazon, which has a flux of 200,000 cubic meters per second. And if you multiply Q by delta G, you have a power which is nearly 1 terawatt. So meaning that the Amazon is dissipating 1 terawatt in the Atlantic Ocean. So, of course, the reservoir is big, so hopefully it's not boiling, but that gives you the order of magnitude. So I just present that because just to give you the idea that this energy is not anecdotal. It's huge, actually. And actually, when you put numbers, it's basically all over the world, a few hundreds of gigawatts, let's say. And this number becomes a bit more precise lately with some more estimates. And this is not small because, for example, all over the world, there is something like 300 gigawatts of nuclear power. So just to give you a comparison. And osmotic energy, so it's renewable, of course, non-carbonated, non-intermittent, which is very interesting as compared to windmills and etc. So that's okay. That's great. The huge question is how to harvest it. And there has been indeed attempts, and one early attempt was done by Statkraft, actually, and using a technology which is interesting. It's very simple in its principle. So it's just if you take fresh water, seawater, you put a semi-permeable membrane, and I come back to that. Because of osmosis, you have a flux of water going to the sea, to the seawater. So you have a flux, and with this flux, you can run a turbine. And so then you produce electricity. And that's cool. Another way to do that, and this has been done in this city, which I cannot pronounce.
It's a dike.
It's that.
There's no connection.
Okay. And where they developed, it's an alternative technique, which is a technology which is called RED, so reverse electrodialysis. And basically, the idea is very simple: is that you have, because of Fick's law, let's say you have a large concentration of salt, you just want to diffuse, but then you don't allow it to diffuse as it wants. You put a membrane, for example. Oh, sorry, I shouldn't touch it. You put a membrane, for example. So I will stay away from that. So you put a membrane where only the chloride ions can go. Then you have only you have a currently this way, and positive. And on the other side, you put a membrane where only the positive ions can go, and it goes this way. So you separate the ions, meaning you create an electric current. So you create an ionic current, which you can transform at the end into an electronic current with a bit of electrochemistry. And okay, so that's the other way. But the key difficulty is that these technologies are too inefficient and also too expensive to just set up the osmotic plant. And I come back to that in details. But one key aspect, of course, is the membrane. And because you need for PRO, for this StatCraft approach, you need a membrane which separates water from the salt. And usually you do that by using a membrane which have a pore size in the range of angstroms. Of course, it's because the hydrated ion is 7 angstrom in size, so you need a very small size. So meaning you can make a simple estimate. I mean, of course, you have a pressure which is huge because the osmotic pressure is 30 bars from between seawater and freshwater, but the permeability is so small that you just kill the power. And actually, typically with PRO and the other technique, RED, typically right now at a large scale, you reach a fraction of 1 watt per square meter of membrane, which is quite small. And actually, there is a number which is, we were discussing this with Signe last time, a number which is in the air is that you have a kind of a profitability break-even, I don't know how to say that, which you should go above 5 watts per square meter so that it becomes interesting to make a real pilot plant at an industrial scale. So right now we are far below that. And so the key aspect is that in this first attempts, people were using commercial membrane, let's say, for example, desalination membrane for StatCraft, I guess, and this anion and cation selective membranes for RED. And these are usually made of polymers, so very expensive. And it's very expensive when you think you need a few millions of square meters of membrane. So that's a huge aspect. And this kills the technology. It's a technology killer. So basically, one of the questions is, can you take benefit of the nanoscale? And so revisit, in some sense, what happens here in the membrane. And that's what is interesting with membranes and like porous materials that you are studying here. Everything is occurring at the very tiny scales, in the angstrom scales, below or in the nanometer scales, but you have to multiply it by millions of square meters of membranes. So you see you have these two infinities which are difficult to assemble. Okay, so that's where I come to what I discussed as nanofluidics. So nanofluidics is basically a domain which has emerged over the last 20 years or less, where basically you study the free transport of water, ionic transport in extreme confinement. So for example, this is a simulation, MD simulation of water flowing in the carbon nanotubes. So basically you want to do that, but experimentally. And okay, so, and then I will give you a kind of a broad introduction of what are the challenges and bottlenecks in this. So these domains really emerged when we started to be able to fabricate things. So basically, you need to do some plumbing at some point. And without plumbing, you can think of plenty fancy phenomena, but you can't do anything. And actually, it happens that we strongly benefited from nanomaterials, so carbon nanotubes, boron nitride nanotubes, graphene, etc. So which I will tell you a bit more. And this. And not only us, I mean, all over the world, there are a few groups which does that. And now it's possible to study transport of fluids and ions in carbon or boron nitride nanotubes down to 1 nanometer in diameter in a very controlled way. And also, I will tell you more about channels in 2D channels, where the thickness goes down to a few angstroms. So, and so just to give you one flavor, so that's how we fabricate systems in Paris. So we use nanomanipulation where under the SEM of carbon nanotubes or boron nitride nanotubes. So this is a real-time movie. So basically, this is a STM tip. You pick up 1 nanotubes in a forest, which you can buy, and you take this and you insert it using a 3D motor inside a hole. And at some point, you see here, you can glue it. And you can glue it with an electronic beam and you crack a gas there. And this you can do by, you can insert it in nanopores, but you can also insert it at the end of a nanopipette, like that. And at the end, once you have, if I come back to this, once, for example, here is a nanotube inserted at the end of a nanopipette, you can seal it. And once you have that, you can really keep the pressure and start measuring things. So that's basically how we started doing a lot of things. So you can do a lot of things with this for carbon nanotube and boron nitride nanotube, I was saying. But then there was this kind of mini revolution inside the field. And this is really thanks to André Geim. So, you know, André Geim got the Nobel Prize for graphene. And actually, in electronics, they develop a lot about what is called van der Waals assembly. So van der Waals assembly is just sticker. We just stick things. So, you know, you can get graphene by putting a scotch tape and taking it out. And that's really how we do in the lab. But then once you have a graphene, which is 1, 2, 3, or 1,000 layers, I mean, it's not graphene anymore, but you can mill it, so take out some parts, and put it on graphite. And then if you put it on graphite, you can put, again, a top graphite on top of it, another sticker. And by assembling this, you do a channel where the thickness is fixed by the number of graphene layers that you have. So you can really go down to 3 angstroms, actually, in size, and in a very controlled way. So that was developed in the group of Geim, obviously, because they have a lot of expertise in these assemblies, and usually for electronics, but that's interesting here for nanofluidics. And that's great, because there you really have systems where the confinement goes down to a few angstrom in an extremely controlled way. And that was really a great opportunity to study many things there. Okay, I will not discuss all that, but I just put this slide to tell you that once you have your system, you start measuring, and sometimes it gives very simple things, sometimes you don't understand. And many times, actually, you don't understand. And there has been a lot of surprise, like, for example, in the group of Geim, they measured a lot of anomalies in the dielectric constant, for example, for water confined in strongly confined systems. And some of these, of course, some of these measurements, okay, many of these measurements we don't understand, I must say. And then, for example, they have done something which is very strange. They took graphene and looked at proton H plus transport across graphene. So, you know, graphene is made of hexagonal systems with a few angstrom in size. So you have a kind of a quantum sieving of, and H plus is the smallest entity that you can imagine on Earth, because it's just one proton. And then it can, according to them, it can cross these circles. So doing a kind of perfect filter. Okay, this is strongly debated. Okay, we can think of many things, but it was nice to see. So, and I will not discuss many of this. It's just to give you a flavor. And what I would like to, I will just present you 2 slides of what do you expect when you go to nanoscales with these experiments in general. So I will not enter too much in the details. I will enter in details later. It's just to give you really an overview of what to expect. So basically, you can take 2 perspectives. So first, you can say, okay, in confinement, usually the good old rules are maintained. For example, Navier-Stokes equation, it works down to 1 nanometer perfectly, you know. And but of course, at nanoscales, you have Navier-Stokes coupled to ion transport, maybe ion correlations, and etc. So you start to mix a lot of phenomena together, and that's where it starts to be very interesting. And just to give you one example, so for example, we did a lot of experiments where we measured the ion transport across these very tiny channels here, a few angstrom in thickness. Usually it behaves very nicely in a simple way, like the current, electric current is proportional to the voltage, so you have a conductance. But in some cases, you start to see response like that. So this is current versus voltage. Actually, this is done in a molybdenum bisulfide system, which is insulating. In this case, actually, can be also conducting, but here it's insulating. And here you see you have this kind of response, very nonlinear response. And this is what usually we call ionic Coulomb blockade, because you have a Coulomb blockade because the conductivity at zero electric field is zero. Sorry, and but starts to raise above the finite electric field. So you can see this response very strongly nonlinear, and also you have a kind of memory, as you can see here. And actually, we could, actually, this was something we predicted before. And the idea is that here it's probably, I say probably because, you know, we are never sure, we have to push it. But it's a signature of the Wien effect, which was actually discussed by Onsager a long time ago, 100 years ago. But here in 2 dimensions, because here your system is really something like that. You have a monolayer of water, monolayer of ions. And when the confinement is insulating, actually you confine also the electrostatic field between the system. And then if you are in 2 dimensions, the electrostatic interaction, Coulomb interaction, is logarithmic, very, very strong. And then, of course, it's very strong. You make pairs, ionic pairs. So, for example, some ions which are strong in the bulk, meaning they separate, they can become weak in confinement. So you make a lot of pairs. And this is boosted when the confinement is insulating, actually. And so we proposed a description where you have this ion pairing. And of course, if you have a pair, it does not conduct electricity. You put an electric field, it's neutral, so it will not move. But then, of course, the positive want to go this way, negative this way. At some point, you will break the pair. And that's the basics of the 3D Wien effect that Onsager explained. And if you do that in 2 dimensions, actually, it's quite different from 3 dimensions. And you have this kind of response. So basically, at zero field, you have a pair. You start pushing the field. At some point, they break. You start to conduct. And again. And then the dynamics come from the separation and reformation of the pairs. And you have memory. And what is interesting there is that once you have memory, you can play a lot of games around what is called neuromorphic calculation, computation. And with, for example, you can do learning with this. This is called a memory store. It's a resistance with memory. And it's extremely interesting because you see you have 2 states of conductance in the system. For the meaning that you can store information there. And okay, so I will not, I could do a full discussion talk about that, but here I will stop there. So it's just to give you a hint that indeed here I just discussed standard physics, so no new physics, but at least you already have some strange complexity occurring, which is extremely interesting to play. Another perspective about what to happen, what to expect at nanoscales is sometimes you see new laws, let's say, new behaviors that you wouldn't expect at all. And so again, I will be very quick on that, but these are experiments that we did 10 years ago, actually, where we looked at the permeability, so really pressure, how much of the flux of water under a given pressure, and in a single nanotube. So the idea was to probe it in a very controlled way in a single nanotube. So we had to use a trick to measure it, but okay, I skip all these details. But what was very surprising is that the permeability of the carbon, you see, is much larger than what you would expect with a no-slip boundary condition, meaning that the classical Poiseuille-Hagen law, or Hagen-Poiseuille, maybe. And you see, carbon is very special. And boron nitride, actually, it's Poiseuille law. Obeys Poiseuille. And boron nitride is interesting because it has exactly the same structure as carbon, except boron nitride is insulating, and carbon, you know, it's semi-metallic. So that was extremely weird, and especially that it occurred in quite large radius. You see 20 nanometers. So that was very strange. And actually, if you translate it into friction, so that's really a measurement of friction of water on the surface, the friction coefficient decays with the radius. Of course, we would love to go to 0. That would be superfluidity. Of course, it will not. But at least you have a strong... and there, okay, I have no time at all. I don't want to enter into this, but what we suggested, and it was the work with Marie-Laure and a great student at the time, Nikita Kavokin, we really suggested that it was signature of quantum friction. Actually, it's quantum, meaning that the water which has partial charges coupled to the electron flux in the system. And you have electronic dissipation. So it's really a many-body effect. And we could explain this kind of curve, actually, versus radius. And I will skip the more discussion. I just wanted to present this because it's really something which were completely unexpected. And here it's the fact that you start to see quantum effect occurring was really not expected. And we have been playing a lot with that. And you can, once you have a new, let's say, a new rule, you have new games to play. And so we played a lot, actually, about energy conversion, float tunneling, etc. But I will skip this part. And we worked intensively with Misha Bone from Mainz and also Angelos Michaelidis from Cambridge in a joint project around that. Anyway, so I just wanted with this, I just wanted to show you that indeed you can expect new things. So and maybe another time I can tell you more about all that. But here, in what remains, I would like to come back to this question of osmotic energy. So come back to the phenomena of osmosis. So more classical aspects, but something which I find always interesting. And osmosis, as you know, has a very, very long history. And it was more or less, I think, discovered by Labénolé in his cabinet de curiosities, which were experiments for people from the aristocracy. And then, of course, the big name is this von Hoff, who could explain the experiments by Pfeffer, and ended up with this trivial but beautiful expression that the osmotic pressure is just a perfect gas expression. KBT times the difference of concentration. And you can see, Dan, that I try to make sure the apostrophe T is
the right place.
Yeah, okay. Okay, you know, osmosis is universal. You can find it everywhere. Even in laundry cleaning, as there was beautiful experiments by the Warren and Stone about that. It was really cool. And what is important is that just always keep in mind that the effect is huge. So meaning the pressure, you take 1 molar of salt and semi-permeable membrane, a pig bladder, if you have a pig, immediately you have 50 bars. So 50 bars is pressure at 500 meters under the sea. So in your kitchen, you have huge effect. So of course, nature has had to adapt a lot to make mechanisms to counterbalance that or use it. I mean, to store energy, it's great. So that's basically the idea of osmotic energy, really, to get this energy back, or desalination. So, okay, osmosis is really what you teach in lectures 101. And the typical situation is typically you have two reservoirs of water with a membrane which is semi-permeable, meaning water can go through, but not the salt or not the solute. And what you see is that the water from the fresh side tries to dilute the water from the concentrated side. And if you have a gravity, this will lead to a difference of 8 in between. And really, the idea, which is explained usually in thermodynamic courses, is that water has the same chemical equilibrium because it can go back and forth. But of course, you have a different salinity. So you have to dilute the part. Or another way to say that, it cannot keep the same pressure. Okay, so that's typical experiments. Okay, at equilibrium, you have the osmotic pressure. You need to push to have equilibrium, or you have a flux if you have a difference. But the point which is very interesting there is that the membrane is the key, but it disappears completely in the von Hoff expression. And that's quite something, actually. And okay, you know, when you teach, you always want to find simple ways to explain to the students. And I always find the thermodynamic approach is always a bit painful, I would say. But actually, looking for a mechanical approach, I went to an argument, and I realized after that actually, of course, the giants already put it 100 years ago. So it's an argument proposed by Peter de Baey, which basically remained completely unknown. And it's a very simple argument where you can find the osmotic pressure in 2 lines, but it's very enlightening, I would say. So the idea is that, of course, as I was saying, you have the membrane properties disappear. So the simple idea is to say, okay, let's make an energy barrier. That's the simplest membrane you can think of. So that's an energy barrier which acts on the solute, but not on water. So water can go through, but there is an energy barrier for the solute. Then, in a trivially, you have a Boltzmann equilibrium for the solute against this barrier on both sides. Easy, so again, 101. Then something which is easy, but actually not a bit subtle when you think to it. You make a force balance. You say, what is the force acting on the fluid on a small slide? And actually, the force acting on water plus the salt is the external force acting on this. So only the force acting on the salt, and you have action and reaction between water and salt. And meaning, so this force is simply the number of salt times the force acting on one salt. And since this is exponential of this times the gradient, an integration by parts gives you in one line KBT concentration. And so it's really trivial, I would say, but it tells you something that basically at the end of the day, the osmotic pressure is nothing more like as the force from the membrane trying to push the solute to avoid it to enter. And of course, when you push the solute, you push the water as well. And that makes a flow. And so I like this force balance because it's simple, but it tells a lot. And actually, you can play a lot with this kind of ingredients of mechanical picture. And so first, let me discuss what is called diffusion osmosis. Because here you see you separate water and the salt, or water and the solute, with a membrane. But actually, do you always need a membrane? And that's the idea of what is called diffusion osmosis, that instead of having a membrane like that, you have a surface like that, and no membrane here. So let me tell you, so of course, we go back to the big man, and to this, so a matrix, a transport matrix, and I was really raised with Jean-Pierre Hansen with this De Groot and Mazur book, and now you have the Bodo Nistrup book. So basically, you have the fluxes, the forces, and you have the matrix of transport. And of course, what is interesting is all these non-diagonal terms, where a lot of physics is hidden. I mean, there. And of course, as Onsager showed, it should be symmetric because of time reversal. And so then, in this matrix, of course, one aspect is electroosmosis. For example, electroosmosis is the flux of water under an electric field. So, okay, you can do the Smolichowski approach, but let me give you a scaling law approach, which will help for the next step. Basically, the idea is that in the electroosmosis is simply the fact that in the bulk, you have no electric force because you have as much ions positive and ions negative. So the force is zero. Close to the electric double layer, here, of course, you have an excess of counter ion. So there is a force only within the double layer. And then this force, of course, will induce a shear flow, shear stress. And this shear stress is nothing but the viscous shear stress, so viscosity times the velocity you will acquire divided by the double length, over which you have a gradient. And this is balanced by QE, I mean, charge times E. And at the same time, the charge is proportional to the zeta potential, which is the surface potential. So if you balance the two, you get immediately the Smolichowski formula. Okay, that's quite standard and it works very well. But now I come back to diffusion osmosis. So here, what I do is I do a gradient of salt. Sorry. And so again, in this matrix, it's a flux versus the gradient of the chemical potential that you are looking at. Gradient of salt, and why does it give rise to velocity of the flow of water? And again, that looks really like an osmosis, but why? And the idea is actually, in terms of mechanics, just like I did before, it's quite simple to understand. Because let's say you have a lot of salt here, meaning you have a lot of attraction of the salt against the surface, because for example, the salt is attracted to the surface. So there is a lot of attraction here, a big attraction force here. Here you have less salt, less attraction. So here you have it's as if you are on an inflatable mattress. So you push a lot here, I'm very heavy, and my wife less, so she pushes less, so meaning you have a flux of air going from the left to the right. So because of this force balance, the gradient of this force, but here along the solid surface and not perpendicular, you have a flux coming over. And this you can put in equation by saying, okay, let's make a force balance on this here. You have the viscous stress along this distance here. That's hydrodynamic stress. And then here now the pressure drop comes from the two ends. So it's KBT delta C, difference of concentration, or acting only over the dye length. So because above, there is nothing like osmotic pressure. It's no separation. So then you have indeed velocity scales like lambda square times the gradient. And for example, for a salt, the length is also proportional to the inverse square root of concentration. So then you can rewrite this as like gradient of log of salt concentration for a salt. Actually, more, let's say, not in general, but if you take a neutral solute, actually this lambda square is proportional to the excess of solute at the surface. So it can be positive or negative. Actually, this argument, this is the first one who started to think about that is Derjaguin. There is a very old paper, 47, where he theoretically thought about that. And this was in the context of Marangoni flows, because you cannot get Marangoni flow on a solid surface. But then he argued that because of the finite thickness of the interface, you could recover a Marangoni flow on a solid. And that's diffusion osmosis. Okay, so you have to do it properly in terms of force balance, but that's basically the idea. And some time ago, when I was still in Lyon, we did some experiments just to highlight that. So for example, that's an experiment where you have channels in the range of 200 nanometer, let's say, in thickness. So small, but not very small as compared to the bilayer, it's very, very small. And we had a way to measure the flow of water. And here it's just to illustrate that for a salt gradient, you have the velocities proportional to the gradient of log of salt concentration. And this works, this is really experimentally shown here. What is funny is that if you take a polymer, but a polymer which is very neutral to the surface, then the effect is reversed. And so meaning you see here, velocity, it goes in this direction. So here it's like this. And this is because the polymer is slightly depleted from the surface because of its finite size. So it's a steric repulsion. So then the mobility scales like minus the radius of gyration of square of the polymer. And so you have a sign inversion. So meaning indeed you can have both signs. And this can be completely explained by the basics. Okay, so it's just the first illustration of going beyond Van 't Hoff, let's say. The second one is about nonlinear transport. So by nonlinear transport, okay, let me come back to ion transport in nanochannels now. So let's say you have a thickness of a few nanometers or more, whatever, and surface charge here. So usually here the typical framework is called Poisson-Nernst plan. It's nothing but diffusion and convection, and diffusion and convection under the electric field, and the Poisson equation. That's difficult. So maybe you want to add flush because it can be important in some case if the Peclet number is not too small, and that's it. And I will come back to that. Something which is very interesting there is that, of course, this equation and Poisson-Nernst Planck are exactly the same that you use in semiconducting system, where people like Shockley and all these people from semiconductors from the beginnings wrote their equation. You write equation for holes and electrons, but the key remark is that what is important for holes and semiconducting systems is that you have the doping. And actually, the doping here is played by the surface charge. Really, I mean, fundamentally, this is how you connect the two. So, meaning that you just take the physics of semiconductors and you plug it on ionic systems. And one thing which is very simple in a semiconductor system is the p-n junction. Of course, it's obtained in the 40s, 50s. And p-n junction means that you have p doping and doping. So meaning in terms of nanochannels means high surface, high or positive surface charge, negative surface charge, actually a charge gradient between the two. Once you have that, you should have a current which is nonlinear, so rectified. And so indeed, that it has been this phenomena has been shown many, many times over the last 10 years or so. And indeed, I mean, for a system, so this was the first one to show that Karnik, where he had a system where two different coatings on the nanochannels. And you can see, indeed, it's a perfect diode. I mean, the reverse current is 0 and very high on this side. And actually, whatever, even with a single channel but conical, for example, it's sufficient to get PN-like behavior. And actually, this is something we showed a few years back with a student, Anthony Poggioli, that whatever, once you have a dissymmetry between the left and right, you have a diode. And the key point is that the key number there is called the Dukhin number, or Dukhin number, if you speak Russian, which is the surface charge divided by the concentration in the bulk, and H is the confinement. So it's really, it has something to do with electron neutrality. So if you are working with colloids, it's really the source of the Donan potential. So it tells you about electron neutrality and as compared to the concentration of the salt. So this Dukhin number appears everywhere in ionic systems. So now let me come back to osmosis with this kind of system. So because, okay, we see ionic diodes, but what about osmotic behavior? And then it's interesting to come back to the mechanical perspective again. So really in the spirit of this simple argument I was showing you. So first, okay, if you have a system, whatever complex it is, inside, you have a local electric force, which is simply the imbalance of positive and negative ions, so the charge concentration, times the local electric field. But now, if I define a global force acting on the system, this will be simply the integral of this force, of this electric force. So the applied what I will call the osmotic pressure, and you will see in a minute why, this is simply the integral of this local electric force. Just as before I was using the solute force. Now, what is interesting with this Poisson-Nernst-Planck is that, of course, at the same time, the total flux of ions, it's simply the gradient of the Fick's law, the concentration, and you have a force which is due to the salt concentration sorry, times the electric field. So then if you replace this term here, this is constant because it's 1D, you have conservation of the flux. So this plus this term is equal to this. So meaning that the applied pressure, or what I will call the osmotic pressure, is nothing but KBT times the difference of concentration, whatever the complexity of what happens here. So that's really in the reservoir, plus the flux of ions. And you see this formula is very simple, and but it's interesting that, for example, if it is completely semi-permeable, you have no ion can go through for some reason. Then this is 0, so you recover the van 't Hoff law. So that's the osmotic pressure. Now, if the channel is fully open, you only have Fick's law. So this is equal to minus this. So the osmotic pressure is 0. So you recover the fact that in this situation, you have both limits which are obeyed. Now, okay, if you want to have a real formula, you have to work a bit, and that's a bit painful, actually, I must say. But you can actually, you will extend the Shockley type of calculation, and you can calculate this ion flux. And what you get is something like that. Okay, whatever it gives, but it shows that the osmotic pressure now is something like the van 't Hoff expression. This is a rejection coefficient, but it's close to 1. And you have a part which is due to the electric field you may apply. And this part is, again, Shockley type, but for the osmotic pressure. And it's a mixture, and when you look at it in detail, it's a mixture of diffusio, electroosmosis, and other phenomena. Okay, so it's just to illustrate, you have versus voltage versus concentration, you have strong, and we verified it in MD simulations, so indeed it was working nicely. So, okay, so it was just two examples to show that indeed this simple mechanical example allows you to push quite well, quite away the concept of osmotic diodes. But now, instead of going more fundamental, I will come back to the more applied side. Say, okay, now you have new phenomena, can you use it? And so this is what I would call voltage-induced reverse osmosis. So as I told you, okay, you have the ionic current rectifier, and we don't know what to use it for exactly, I mean, at large scale. But here you have an osmotic diode. So it's interesting to manipulate flux, and actually, when you think to it, and I will show you in a minute, you can use it for desalination. And that's the main, of course, filtration in general. So let me, so it happens that, okay, this was a null prediction we had, and I was really looking for a system where we could highlight it. And at the end of the day, so a few years later, we realized it's extremely easy to do. So the idea is that you see, you just need a system with two different sides. So actually what we did is simply glue two membranes together, more or less. And so, for example, what we used as one example of a composite system, it's a membrane made of polycarbonate and graphene oxides. Polycarbonate here is just a membrane with big holes in the range of 20 to 100 nanometers, so really big. There is a surface charge. So you have electroosmosis, you have all that. And then on top of that, you deposit graphene oxide. So graphene oxides, it's like a millefeuille, like the pastry. And the thickness between the layers here is in the range of a nanometer. So it's a very good filter that you can cook it in your kitchen. So that's very easy to do. And then you see, you have a part of the system which is non-selective, but a surface charge, very big pores, and a part which is highly selective, and tiny pores, no very small surface charge. So then indeed you have a gradient of this Dukin number here. So this should rectify. And so what we did as a system, so okay, that's typically an experimental setup, but it's just a cells where you take this, you sandwich it between two electrodes. So usually we use carbon electrodes because they are extremely and very standard. And you just press it and you put voltage in between, and you start measuring whatever. And indeed, what you see is that the flux of water, so this liter per square meter per hour, across the system versus the voltage is, I mean, in particular for this small, but not too small nanopores, 25 nanometers, is very asymmetric. And so indeed, that's a demonstration of this rectifier. I mean, and actually, another way to show that is to play with AC voltage. So instead of applying a direct current voltage, you play AC. First, I show you what happens with only the polycarbonate. So that's polycarbonate means there is no, it's a single electrode, so it should go one way or the other way. And indeed, okay, when you go forward, backward, nothing happens. But then if you start to add carbon nanotubes, graphene oxide, you see it goes where? It goes on the other side, stops, goes on the other side, stops, and you see rectification here. So that's and this is a flux versus time, and you see that it does not go on the negative side. So you really see a rectification. And so you have a rectified water flow, so an osmotic diode. And so this you can play with that, because now you can do filtration. Because, for example, graphene oxides has a pore size in the nanometer range. So meaning you can filter out whatever is above 1 nanometer. And so here, just to illustrate, we did with the rhodamine system, which is 1 nanometer in size. And there it's oscillating, but at 2 hertz. So you won't see the oscillations. But okay, it's just to, if it works, it should be a movie. So just to show that actually it filters out, of course, because graphene oxide is filtering the stuff and you are pushing it. So indeed, under an oscillating voltage, you see it decreasing and this is increasing. We had to do many films like that because the referee didn't believe. So anyway, so I have other films maybe which are more explicit, but indeed you see it works and it filters out because there is nothing it can do otherwise. Okay, I will skip all the discussion about what is the optimal frequency and etc. because there is an optimal frequency there, resonant like, but whatever. And what is nice there is that you do this filtration here for this rhodamine, but okay, you can choose the selective parts. So we played a lot for sure with graphene oxide and MOS2 because they are easy to fabricate in the lab. But you can also use polymer membranes which you glue to the polycarbonate membranes. And there, these polymer membranes are desalination membranes. So meaning then you can really desalinate actually. And so what are the performance? So first, very quickly, selectivity. So for example, it's whatever you put pressure, you put voltage, is the same, of course, because that's the selective part which plays a role. And so for example, we played a lot with micropollutants, so hormones and things like that. And for desalination, okay, graphene oxides and MOS2 are bad, of course, to see because the size is 1 nanometer. So they sieve a bit the salt, but not too much. But then when you use a commercial membrane, of course, the rejection reach 100%. Okay. Just as for pressure driven, it just works the same. Now, what is much more interesting is a kind of, I would say, flow efficiency. I will not speak about energy efficiency. But the question is, okay, you do an experiment with pressure and you push, let's say, 10 bars. And for example, for desalination, you have to push above 30 bars. How much volts is equivalent to that? So for example, in this first experiment that we did, I think with MOS2 and graphene oxide in this system, actually, so let's say you have a flux under a given flux under a pressure drop, and here you have the same under a given voltage. So you can ask for the same flux how much voltage I can get, I need. And actually, it happens that for these experiments, typically you have in the range of 1 volt is equivalent to 1 bar. But actually, by playing with the geometry, and actually it happens that if you reduce the size of the polycarbonate membrane, you boost completely this performance. And we went up to 1 volt is equal to 15 bars. So meaning that you could do nearly desalination at 2 volts, which starts to be very nice because 2 volts is a photovoltaic cell and whatever. I mean, so that's what we started to play. And now the rest of the adventure now is that, of course, this is lab scale. And lab scale, we can do that, okay, at most. That's what we do now. But in the lab with this, but what we really want to go is this, and so this we cannot do in the lab. So typically the way we do is to create a startup, and there are these two guys, Zachary and Lucy, who have now developed a startup, and now it's really efficient. And I come back to that for osmotic energy. It's really efficient in terms of transforming what happens in the lab into what is useful for the society. Because they have a mission which is create that. And honestly, after they live for 6 months, and they are nearly there. I mean, so meaning that they are extremely efficient they have screened all the materials you can imagine. And you know, for membranes, they have huge handbooks of membranes. So and they did a lot of work, and I think it's working efficiently. So hopefully, in a few years, they will be able to plug this kind of thing with voltage instead of pressure. Okay, so that was just an example of this story of osmosis. And now I come back to osmotic energy. I will take only less than 10 minutes again. Okay, so the point is that I told you before that one key aspect was what happens to the membrane for osmotic energy with these two techniques, if you remember, PRO, pressure retarded osmosis, and reverse electrodialysis. So it happens that the first experiments that we did was about osmotic energy, but the first nanofluidic experiment. So that was experiments not with carbon nanotubes, but with boron nitride nanotubes. And this boron nitride, again, I was saying, it has the same structure as carbon, except same crystallographic structure, except it's insulating. And we put a difference of salinity between the two ends, but here with a single nanotube. Okay, we didn't care about the membrane. So, and then what we could measure the osmotic current versus the concentration ratio here. And indeed, you measure ionic current. Here, for a single nanotube of boron nitride, it was the nanoampere range. So nanoampere is very small, of course. But look, if we do the same with a pressure drop of 1 bar, we get picoampere. So for us, it was very large. So when we saw that. And of course, this is corrected from the Nernst potential and etc. But whatever. Now, okay, so that was very surprising. And okay, if you convert it in terms of an osmotic power, so basically it's I mean, you imagine putting a resistor outside and you measure the maximum power you can extract. You get a power in the range of 1,000 watts per square meter. With the idea that you put a lot of these nanotubes, okay, just multiply foods here and bread. But okay, so this means that the power, if you multiply it, you would get huge number. And so there are two things which are interesting there. That first, at that time, it was slightly unexpected to measure an osmotic current because here the nanotube diameter is very large, so the radius is 40 nanometers in this case. So you see, you shouldn't have any osmotic pressure, but you have a current. And of course, if you remember what we discussed before, that's a question of diffusion osmosis, actually. And because, as I was telling you before, we discussed the fact that if you have a gradient of source, you can create a velocity. But this velocity will carry on the charge within the bilayer. So you create a current, and an ionic current. And this ionic current is simply, in some sense, this velocity times the surface charge, more or less. Actually, it's slightly more subtle than that if you do the proper calculation. This only occurs when the surface charge is very high. And when the surface charge is very small, you have basically nothing. So that was the second miracle of this experiment, is that it happens that boron nitride, and that was completely unexpected, has a huge surface charge, up to, in the fraction of coulomb per square meter, up to 1 coulomb per square meter, knowing that glass is the 20 millicoulomb per square meter. So this, it was very surprising. So we were lucky to have a material where you have a huge surface charge, and on top of that, you have this diffuse osmotic transport which drives the current. So you don't need very small nanopores. And about the surface charge, I think maybe Myla will tell you more later, another time, because she has been doing a lot of simulation to understand where these surface charges come from. And a priori, it comes from the chemical absorption of OH minus on the boron nitride to do a bit like a boron acid, boric acid. Sorry, I'm not a chemist. Anyway, so that was too luck, let's say. And so, okay, once you can screen materials, once you have something, so there were colleagues from EPFL who looked at MOS2 materials, where they dig single nanopores, the group of Radenovic, and they actually measure even 1 million watts per square meter, megawatt. And actually, I will come back to that. We played a lot with materials. One, of course, carbon would be the great material because carbon is easy to fabricate. We already have many situations where, and actually we looked at what we call activated carbon, so or altered carbon. A book about that. Anyway, and activated carbon just means that we put it under an electron beam, or basically you put it in the plasma, the cleaner, and this raises a lot of chemical groups at the surface, and there, this carbon leads also to very large power. Now, of course, all of this is at nanoscale, I'm going to say, but it's interesting because when you look at the literature, there has been a boom over many different attempts, and basically people take whatever is on the shelves and try to measure an osmotic energy. And you have silk somewhere, you have mushroom-shaped nanochannels, so what they call bio-inspire, I think it's silk, but there are many aspects, many in China. And actually, what was interesting is this one from the Pense et al., where they were able to fabricate membranes out of boron nitride system. And so, because we were looking at single nanotubes, but these membranes were also very highly efficient, in agreement with what we found for the single nanotube. Just, okay, so what I find interesting is that there is an excitation to find new materials. And so that's where you have a revival of this osmotic energy, because instead of going only to, let's say, desalination membrane or standard ion and cation and anion selective membrane, you explore many materials. And the fact that you have diffuse osmosis instead of bare osmosis means that you can have pores which are extremely large. You don't need extremely small pores. So this opens completely let's say, the space for the screening. And that's, the problem is to scale up, really to scale up. Because here, for example, that's the paper by Pense I was discussing. So they looked at the power density versus the membrane area. And okay, so we are around here. And actually, you see it's decreasing. And there are very good reasons for that. But if you put numbers, here, this is 1 centimeter membrane. And you want to have 1 million square meter. And so there is still a huge gap. And in practice, you want to have this kind of break-even of 5 watts. So 5 watts, actually, it's here. And you see most of these materials are completely unable to bypass that. So, but actually, okay, I like this picture, but it shows that I think it's a good metaphor for physics. I mean, we like to draw this kind of stuff. That's my level of drawing. But at least you take only the few ingredients, and that's sufficient. Here you need high surface charge and diffuse osmosis. So basically what you need. It's very simple. And so we have been screening many materials to try to explore. So I showed you carbon, activity carbon. For example, we looked also at titanium dioxide, which is very interesting, titanium dioxide, because it's an anti-fouling system. For example, Saint-Gobain has windows which are anti-fouling, and they put titanium dioxide. And usually anti-fouling means that large surface charge, because the biological entities, they don't like high surface charge. So that's why and titanium dioxide was working very nicely again. But we tried many aspects, and but then I will go to make a huge jump in. I will stop in 1 minute. We make I'm 57 minutes. And so what we did actually is to, again, that was 10 years ago, we co-founded a startup with some guys who were a bit crazy to believe us. And they did incredible work. I mean, so we first worked together to screen materials. And at the end of the day, they found, because you look at everything, but they explore many materials, but one which is very interesting, it's a modified cellulose. So it's a nanocellulose, so it's a specific recipe, but it's cellulose, so it's paper. And with this modified cellulose, which you see, this is in Finland, actually, you can produce it by thousands or millions of square meters. They were able to develop. Initially, this was this kind of, instead of a single nanotube, this was this kind of osmotic cell. So you see, and now what's interesting is that in last year, so maybe I should show that, with their new materials, and actually you have to be careful also for the design. In a multi-layer system like that, which looks a bit like the LED, they were able to bypass, they were above 6 watts per square meter. But for industrial systems, so meaning that's typically the module which they have, where you have hundreds of square meters or whatever. And the key point was really to search for this material in line with what we have been discussing, so diffuse osmosis, large charge. And but then there is a lot of engineering and science together, because you have to chase all the electric resistance everywhere in the system, and that's what they did. And now they have a pilot. Okay, StatCraft had a pilot on the fjord here. It's a pilot close to the Mediterranean Sea, close to Marseille, where you have the Mediterranean Sea and the Rhone coming over. And now they are producing, of course, slowly. It's still an industrial pilot plant, but I think that's the first step. Okay, so I think I'm done. So 60-0. Thank you very much.
Can we start with questions? Maybe also from Oslo. If can you switch on the sound? Sure.
No, it's on now. It's on. They unveil.
Does anybody there have a question? Yeah, Eric?
Oh, we don't hear you.
We can't hear you.
Oh, there is a guy from the European Games coming in.
We still don't.
Is it on?
Now? Yes.
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 Can you hear me now?
Yes.
Okay, this is Eric Bocquet from Oslo. Thank you very much for a very interesting talk. I was especially fascinated by the enhanced permeability in carbon nanotubes, which you ascribe to quantum friction. Is this an effect that has been observed in other contexts of small-scale flows?
So you mean other systems other than carbon nanotubes, you mean?
Yes. So is it particular for water in carbon nanotubes or?
So, okay, so carbon is very, very special. So that's where, to make a quick summary of what happens, the fact that the friction on water is small is actually not so surprising because carbon is extremely dense, in particular graphene or whatever. So actually water sees something very, very smooth. So the friction, the corrugation should be small. Now, in some sense, the big question there actually is reversed. Why it is so high on graphite? And in our experiments, we had a multi-layer carbon nanotubes. And the point is that we showed that we are thinking in terms of excitations and modes. It happens that water modes, so which is the Debye peak of water, which is gigahertz to terahertz, can couple to one plasmon modes of graphite, which is in the same range. And this occurs only for graphite, but not for graphene. And this plasmonic mode has been measured in various experiments, even in STM. So it has been shown experimentally. So that's very specific to water and carbon interface. But so that's why, in some sense, we could find it in this system. Now, in the lab, we are working on plasmonic systems to tune a surface where you can tune the plasmon. And we are working with a colleague who works in the terahertz range for telecommunications, actually. And there they have terahertz plasmon, very controlled. And so experiments are just ongoing now. So I don't have the answer, but I think it could be generalized. But right now, we have only this strong indication only for carbon.
So is this something you could see as a slip boundary condition, say by
yeah, totally.
It's techniques or things like that?
Yeah, totally. So okay, usually I show a plot of slip length versus radius, for example. And indeed, this friction actually is inverse of the slip length. So it's really a slip boundary condition.
Right. Oh, thank you.
So that means you actually have the same friction in a larger system, you just don't observe it because it's relatively much less important.
You have the same friction, sorry, in the larger systems?
Yes.
Yeah. So for example, in the plot I was showing also flat HOPG. So they were independent measurement by colleagues who looked at using AFMs, they looked at the slip length actually of flat graphite, so infinite radius, let's say. And the friction actually is compatible with our largest nanotubes, multi-wall nanotubes of carbon. And so I don't know if this answers your question, but that, yeah. So indeed, if at some point, if you are large enough, it's as if it was flat.
Just a follow-up.
Yeah.
Do you think that it's mostly because of mechanical effect, because it's a flat surface? It's not because it's confined.
No. Yeah. So actually, no, but that's a very good point. And actually, initially we thought it was because it was confined, the water confined, etc. But when we dig really into that, and actually, even with simulations and theory, but you can find an effect only when the diameter is in the range of 2 nanometers, something like that. So very strongly confined effect occurs really at the smallest limit. But here, what was very, very strange is that we observed it already for diameters which were 50 nanometers, something like that. So that was very strange. And actually, in terms of this excitation, you can explain that, because the point is that the 50 nanometers radius, they behave like graphite, but it was shown by Dresselhaus at MIT and others that when the carbon nanotubes get smaller and smaller in radius, the layers decouple from each other. And actually, at some point, the first layer in contact with water decouples completely from the other. So it looks like graphene again. So you don't have this plasmon anymore. So that's why you have a radius which dependence, but this is at least within this understanding, at least. But this explains why you have a radius dependence, but already in the range of 20 nanometers, 30 nanometers, which was very unexpected, right?
Thank you so much for telling us how to make the cross coefficients come to play and be important. That was nice.
Thank you.
One of one of the systems you mentioned relatively early struck me. I think you said that for the dielectric constant, there is an anomalous behavior. And of course, geometry is a parameter when we now speak about nanofluidic systems. So my question is, did you try to find scaling laws? I mean, we tried water at the surface, and the surface tension of water when you shrink the system very low down is still regular. It's inverse to the
radius,
size of the system.
And okay, this was the work of the group of André Geim and Fumagalli, actually, but so we didn't do this work. But actually, there are two aspects. One aspect is that it's from their measurements where they see the, show it again. I think this is a curve. Oh, it's not here anymore, so I will share it again. So this is the curves of Fumagalli in two papers. The first paper was this one, the bottom one, where the dielectric constant versus water film thickness goes down, and you see saturates around 1 nanometer or something like that, at a limit of around 2, so the optical limit. It happens that this first behavior here, where maybe I shown here, this first behavior here, it's really nothing more than a capacitor, where the surfaces have a low dielectric constant. So that's something which is not clear, but at least that's how it behaves. And then you have the bulk. So you have 80 and 2 within a few angstrom, and that gives you this kind of scaling which is here. And then it saturates, and you have some signature here. But so that's the dielectric constant perpendicular. And the dielectric constant parallel to the channel. So that's their latest measurements, and this behaves completely differently. You see there is a jump here.
Yeah.
And this, honestly, I don't know.
Yeah, but there is a rationale for that scaling.
I don't know.
In the nanothermal.
Oh, you okay. But then I mean, if you could explain this, that would be great, because for now, I don't think they have an explanation. Because I think the best they can do is this dashed line here, which was not